Chapter 2, Acids and Bases. We're going to talk about acids and bases from the perspective of organic chemistry. Now, specifically in organic chemistry, an acid is something that loses a proton, but a base is something that gains a proton. Now, when we're talking organic chemistry, we're primarily talking about the acidity and the basicity, but we're talking about it in terms of nucleophilicity and electrophilicity. So we're looking at nucleophiles and electrophiles. Now, acids come in different strengths. You have your very strong acids that have pKa values less than 1. You have your moderately strong, weak acids, very weak, and extremely weak acids. So the stronger the acid, the larger the Ka. The stronger the acid, the smaller the pKa. Remember, your P function, pKa, is going to be equal to the negative log of the Ka. So the greater the pKa, the weaker the acid. Now that's going to be very important in organic chemistry. Now remember, your pH is analogous to pKa in that they're both P functions. And what we have are some of the more common organic acids. So you have a carboxylic acid, and that's the most common organic acid. And the acidic proton is right here, and this acetic acid has a pKa of about 4.76. Now on our scale that we just talked about, that ranks in weak acids, but it's one of the strongest organic acids. Organic acids are considered weak to extremely weak, but we need to know the difference. Now, alcohols, and we're looking at this proton right here, they have a pKa of about 15.5. So again, on our acid strength, now we're looking at extremely weak, 15.5. And those are some of our strongest organic acids. And then from there, the pKa values get even greater. Amines have pKa values on the order of 40. Protonated amines, on the other hand, are much more acidic with smaller pKa values. The smaller the pKa value, the more acidic the acid. Now, some of these compounds, some of these functional groups that we're talking about, and we'll talk specifically about functional groups in the next chapter, but some of these groups can be amphoteric. Remember, an amphoteric substance is something that can act as both an acid and a base. So what we're doing is using the lone pair here for it to act as a base to abstract this proton. It depends on the pKa values of what you are reacting it with. So the reactant that behaves as the acid is going to be the stronger acid, the one with the smaller pKa value. So the smaller the pKa value, the stronger the acid. So in this case, between these two reactants, the hydrochloric acid with a pKa of -7 will act as the acid. And between these two reactants, you have ammonia with a pKa of 36 and water with a pKa of 15.7. The water is going to act as the acid. Now, equilibrium is one of those topics we talked about in general chemistry, but in organic chemistry, you might need to decide which way an equilibrium is favored. And equilibriums will favor, when we're talking about organic acid-base chemistry, they will favor the formation of the weaker acid. The weaker acid. Remember, the weaker acid is going to have the higher pKa value. So you look at your reactants and products and find the pKa values. So here you have a pKa value of 4.8 and here you have a pKa value of 9.4. Therefore, the equilibrium will favor the formation of the weaker acid, and this is all based on stability. Electronegativity also affects pKa values. So the more electronegative, the stronger the acid. And the reason for that is because of the charge separation. The more of a charge separation there is, the easier it is for that hydrogen to be abstracted. And that explains why alcohols are stronger acids than amines, because the electronegativity of oxygen is greater than that of ammonia. So there's more of a charge separation between oxygen and hydrogen than there is between ammonia and hydrogen. Now, the hybridization of the atom also affects electronegativity. So the more S character the orbital has, the more electronegative it is. Now, all other things being equal, the size of the atom will also affect a pKa value. The larger the atom, the stronger the acid. Now, all of that can get rather confusing, and there's a homework problem that will address some of this so that you can practice. But having the pKa values is really the definitive way to determine what is the stronger and the weaker acid. Because when you start getting into it, the substituents will also affect the acid strength. Now, a substituent is the part that is not, here, let me use a different color. The substituent is the part outside, the part hanging off. So here we have methyl, we have a methyl bromide, we have methyl chloride and a methyl fluoride all hanging off this carboxylic acid. So looking at the pKa values, you can tell that this is the strongest acid. Well, this fluorine has the most electronegative character of all four of these substituents. Therefore, it will draw the electrons towards it stronger and lower the pKa value. That's called the inductive electron withdrawal effect. So in all, and I know that was an awful lot to take in, summarizing the factors that affect acid strength. As electronegativity increases, the acidity will increase as well. As size increases, the acidity will increase as well. When it comes right down to it, look up the pKa values and you'll be able to tell fairly easily. Now also, hybridization, the stronger acid is going to have more S character. Fewer orbitals in the hybridization. More orbitals hybridized, the weaker the acid. And then we have the inductive electron withdrawal effect. So the greater the electronegativity of the substituent that is withdrawing the electrons, because that increases the stability of the conjugate base, then the stronger the acid. Now you will also have to determine at some point whether a compound is charged or is it neutral. Is it in its acidic form or its basic form? And again, that answer is going to be in the pKa. If, for example, the pKa of this carboxylic acid is 4.76 and we are at a pH of 10, then the form of our carboxylic acid, we will actually be in the basic form because the pH is greater than the pKa. Now there's also a homework problem based on the various definitions of acids and bases. So we have our Lewis acid and base, and what we're talking about is the sharing and donating of an electron pair. Now in organic chemistry, we primarily use the Lewis acid and base definition, but we call them nucleophiles and electrophiles. Now, an acid is a proton donating acid, where a Lewis acid is a non-proton donating acid, so that's something that is going to accept an electron pair. A nucleophile is a compound that's going to share its electrons. It likes the nucleus, it likes the hydrogen, and those could be things that have a negative charge, or they could be things with a lone pair of electrons.